Great. I welcome you all in Day 6 AI for Monitoring, Reporting and Verification Climate Change AI Virtual Summer School 2024. Our main supporter for this summer school are Google DeepMind, GitHub, CIFAR, and Mila. Climate Change is a global nonprofit organization that realizes impactful work at the intersection of climate change and machine learning. If you want to know more about us, you can visit our website, that is www.climatechange.ai. You can also follow us on the Twitter, that is at the rate of climate change AI. You can also join our community and the newsletter by visiting our website. We welcome you all to join our today discussions. You can join the chat section for general comments, and you can ask questions using the Q&A features. Upvotes the question that you are most interested. Due to high number of participants, we might not be able to address all the questions. So the question with more upvotes will have a higher chance to be addressed. Also click on the show caption to enable your captions. All participants are required to abide by CCAI Code of Conduct. In case of any situation arises, please report at the rate of climatechange.ai. The schedule for our today lecture is the lecture will be starting at 10 a.m. That is AI for monitoring, reporting, and validation of GHG emissions. Our today's speaker is Dr. Kasia Tokarska, and myself, Tariq, and Olovo Fremi will be the assistants for our today's session. Dr. Kasia Tokarska is a seasoned climate scientist with over a decade of experience in analyzing Earth system models and climate data. She earned her PhD in climate modeling and gained postdoctoral experience at ETH Zurich and the University of Edinburgh. Prior to joining Carbon Pool, she held several positions at climate risk startup and McKinsey. Her expertise include exploring climate system interactions and statistical climate data analysis. Kasia is particularly interested in applying interpretable and physically informed machine learning techniques to enhance the robustness of policy relevant matrices to enhance the robustness of the policy relevant climate matters such as emissions accounting. Currently, Kasia is working as a principal climate modeler at Carbon Pool, where she's leading the climate risk analysis about carbon removal projects. So without any further delay, I'm excited to welcome Dr. Kasia Tokarska to lead our today's session. Thank you. Welcome, Dr. Kasia Tokarska.
Hi, everyone. I'm just going to share my screen. Can you see it well? All right. Yeah, it's a pleasure to be speaking today about machine learning for emissions accounting and monitoring, focusing both on the industry sector and also on the country level emission reductions national targets. So as we deep dive into this lecture, I first would like to show, maybe like briefly summarize the experience I have. So as it was mentioned in the introduction, I have a PhD in climate modeling, but I also did a lot of postdoctoral research at ETH Zurich and University of Edinburgh, working with different climate models and also machine learning applications to analyzing climate data. And after that, I've been also working in the industry experience, including like climate risk modeling, different regulatory kind of perspectives that industries need to meet for climate risk regulation in terms of disclosing physical and transition risk. And currently, I'm working in the carbon removal sector, so I'm working with carbon offsets and specifically carbon removals and nature-based solutions, providing insurance for the different type of removals at Carbon Pool. So my interest in climate change AI community is kind of bridging this machine learning and climate science communities and creating collaboration opportunities. So also feel free to connect with me on LinkedIn, and if you're looking for like to catch some advice in terms of either working in academia or industry, I'm always happy to connect with people and see what could be helpful for them. So now if we look into today's lecture, there's going to be 3 parts of the lecture. The first part is going to be kind of the motivation for emission accounting. Why do we even want to account emissions? and what are the different ways of doing it. In the second part, we'll deep dive into the methodologies, how we can actually account for emissions using different approaches. And then finally, we'll look into some applications of machine learning for emission monitoring. And then we'll also discuss the future challenges and directions. So maybe let's start with the motivation, which is here that in this section, you will learn about physical and transition risk. What is actually the greenhouse gas emissions accounting for the industry, and what's an example, for example, of scope 3 emissions accounting. So as I mentioned, like the first question we want to answer is like, why would we even care about emissions accounting? So we know that emitting carbon dioxide to the atmosphere causes a lot of both physical and transition risk. By physical risks, I think it's maybe easier for you to relate to. It's like any kind of different events. It could be like extreme events or chronic events that are happening due to climate change. It could be intensified frequency of wildfires, heat waves, hurricanes, drought, sea level rise, flooding, and many other impacts of climate change that are being experienced in different locations. And as you can, I think both on a country level for different countries and for different industries, those risks can pose immediate kind of negative consequences for the businesses, right? Because if you have a flooding, maybe you have to shut down the business. Maybe if there's a heat wave or a wildfire, again, there could be like immediate direct negative consequences of those physical risk impacts. But in addition to this kind of physical part of climate change, there's also transition part of climate change, which means for both for countries and for industries individually, they may face different risks due to policy regulation changes, liability for contributions to climate change, or for greenwashing. There could be also market shifts. For example, customers prefer to buy more sustainable products. There are lots of reputational risks. So companies who maybe don't decrease their emissions may face reputation loss, and then also there's like different technological risks that are related to it. So there are benefits in reducing emissions both on country level and national and like individual kind of company level due to like this direct avoidance of physical risk, but then also due to like avoidance of those transition risks that can happen to the company if they don't reduce emissions. And I'm sure a lot of you have heard about all the net zero targets that different countries and also different companies individually declare, whether it's by the year 2030, 2040, 2050, there's different years they want to reach net zero. And what it means, it means that the total emissions in a given year of a given company or country should be zero. Of course, it requires a lot of reduction of the emissions. So whatever could be reduced, it should. So for example, this could be initiatives such as switching to electric cars instead of gasoline cars, or switching energy provider to a more green provider. But even if you do all those possible initiatives you could do, you might still end up with emissions that are difficult to abate, or you cannot be really fully responsible because those emissions come from some source you cannot easily reduce those emissions. And in that case, you need to remove the remaining emissions you're responsible for. And that's why we have carbon removals or carbon offsets, especially removal ones are very important because they actually remove CO2 from the atmosphere. So that's why emission accounting is very important here, because in order to know whether you're not zero or not, you need to know first, well, how much I'm emitting, what can I do to reduce the emissions? And if there's anything left over, as you can see here on this example, so the ones on the positive side of the graph, you can reduce, so those bars becoming smaller. But then also you're buying offsets, so it means you also kind of offsetting the emissions you were not able to reduce. And in that case, you can be fully net zero by kind of both reducing and removing emissions at the same time. And you can see probably a lot of bar charts examples like this for different companies and also for different countries. So that's why here, like, it's really important to know what are the different ways to account for emissions in order for you to reach net zero. And if we think about the different sectors, where do emissions come from? A majority of the emissions right now come from the energy sector, over like 70%. And you can see also there's a large portion of emissions coming from the agriculture and forestry and land use sectors. And there's also emissions from the industry sector, especially chemicals and cement, which are quite difficult to mitigate, and also landfills, wastewater. So there's a lot of different contributions to the global emissions, and then each of them would also have different ways of mitigating and reducing them, depending on the source of those emissions. If you think about, especially on a company level, how they account for emissions, they look for scope 1, 2, 3 emissions. And this is kind of like a category of like, how can you bucket the different type of emissions you have? So looking at those different categories of emissions, scope 1 is like your direct emissions from your company. Scope 2 would be emissions from your purchased electricity. And then scope 3 would be like indirect upstream and downstream emissions from the different categories as shown on the slide. So which do you think for a given company is the biggest source of emissions? Would it be scope 1, scope 2, or scope 3? So hopefully everybody can vote and we can see the results soon. Okay, could we maybe see the results once people vote? Okay, great. So we can see that like some people think it's scope 1 and 2, and then about half of the people think it's scope 3. And this actually, I mean, to be fair, it really is company specific. For majority of companies, scope 3 are the largest part of the emissions. However, that's not the case for all companies. So for example, if you're oil and gas company, then your direct emissions will be mostly scope 1, right? Because you directly create those emissions in your production process. But for a lot of companies that rely on the scope 3 kind of supply chain and business travel and all the upstream, downstream emissions, you see there's like a lot more categories in scope 3. So once you start adding it all up, it becomes the largest source of emissions. So the answer to this question is like, yeah, it is very company specific. And for majority of companies, it will be scope 3, unless they are like maybe oil and gas or some other sectors that are directly contributing to the emissions. So what is really challenging, because scope 3 now is the biggest contribution of emissions, it's also the one that is the hardest one to kind of mitigate or have control over, because a lot of those emissions you don't directly own. It's somebody bringing you some product you use, or you're using the airlines to fly, for example. So like you cannot directly say, oh, I'm going to only fly electric planes, because then you would have to own those planes, right? If you just go and travel for business, you can't, well, you can choose how you travel, but like it becomes more difficult to have control over those scope 3 emissions. And that's why it's like a major problem in decarbonization strategies, that like limiting those emissions is very challenging. So if we move further, yeah, we actually just had this question. We can look here on this graph, which can like this figure really maybe like listed in a different way. But if you think about the direct emissions would be your scope 1 and 2, and then the indirect, direct one would be scope 1, and then scope 2 and 3 would be indirect emissions, which you have some control over where they come from. You can change the supplier of your electricity, cooling, for example. You can change supplier of your purchased goods, but sometimes it's really difficult. So, and also it's very difficult to account for it, because you need to ask your suppliers, what is your emissions, right? So you can see all the challenges in accounting those emissions that way. So now maybe like, let's just give an example of a kind of hands-on. Imagine you're running an ice cream company, which is called Earthly Sweets, and you're distributing ice cream to different supermarkets. You want to be net zero. So in order to be net zero, you need to account for your emissions scope 1 to 3. And what could be examples of your emissions? So like, let's say for scope 1, you're running a fleet of vehicles, so you can kind of directly calculate how those vehicles are emitting. And if they're electric, of course, your emissions would be much lower. You maybe are also heating up the spaces. And again, it might, like if you're using on-site boilers, it might be creating emissions. If you're changing to some other electricity, maybe based a green energy source, then again, you can reduce your emissions in this way. And maybe you have emissions from the refrigeration equipment that is used to keep the ice cream cold. So in total, you have some number of emissions. Then for scope 2, again, you can have some electricity use. Of course, you need electricity to power it all. And you can choose an electricity company that is like renewable company. So maybe you can reduce your emissions this way. And then this includes like, lighting and conditioning, keeping everything cool. So those two scopes in this case would be somewhat relatively easy to maybe monitor, and also to reduce the emissions and make them all net zero. But then for your scope 3, again, like what would be some examples for this company of scope 3 emissions? And how could you potentially reduce them? Like if you think about like, if you have an ice cream truck with ice cream, what could be examples of your scope 3 emissions? Okay, maybe we can see some of the answers. Okay. Okay, I can't really see the answers, but okay, maybe we have a way later to check them up. Okay, maybe then we can move on. So yeah, okay. Okay, I don't know. All right, so so maybe let's move on and then we can check the answers later because they don't display. All right, so here, for example, of course, business travel would be one. So if you go to some ice cream conferences or you take flights, there could be one example of scope-free emissions. If your emissions, you have emissions from employee commuting to the office, there could be another kind of source of emissions, which maybe you could mitigate by encouraging everybody to use public transit, for example. You could maybe have emissions from production and transportation of the raw ingredients that make the ice cream. If, for example, you get milk delivered from somewhere else. So again, in this case, those emissions are really difficult to reduce because you rely on this product and you could change suppliers, but if there's no other options of other suppliers, it'll be really difficult to reduce those emissions. And as you can see in this case, because it's a kind of consumer-based company, scope 3 is by far the largest contribution of emissions rather than scope 1 and 2. So if you think about it in terms of additionality, it's actually interesting that scope 1 emissions of one company are becoming scope 3 emissions of another company. So there is some double counting happening, right? Because all those scope 3 emissions that you have to account for, like where your product, like, like the products you use for your production, where do they come from? Those emissions are actually scope 1 direct emissions of someone else. And this is kind of like it's an example showing that like this for all those companies, the scope 1 emissions are listed like kind of like here, and then they could become also scope 3 emissions of someone else who's using those products. So like if you're a mining company, you have scope 1 emissions, but then also like if you like someone else buys those mining goods, then this becomes someone else's scope 3 emissions. So in principle, if everybody reduced the scope 1 emissions and became truly net zero, scope 3 emissions by default will become zero as well. But unfortunately, the reality doesn't work this way. And in order to encourage everyone to become net zero, right now, everybody kind of has to double count and reduce both your scope 1, 2, and scope 3 emissions. So here is kind of a contribution of scope 1 to 3 emissions for different industries. And as you can see, like as we mentioned earlier, scope 3, this is like scope 1 and 2 are like the light green ones. So they are like, for utilities, maybe you'll be half and half. But for all the other ones, scope 1 and 2 are relatively small contribution. And then different categories of scope 3, as we discussed, like, for example, employee travel, business travel, and like all the other kind of like upstream, stream, and downstream emissions are like a large contributor to individual emissions for the different sectors. So in the second part, now we're going to learn more like how do we actually account for those emissions? Now we know where they come from. How can we quantify them? So there's some traditional bottom-up approaches, right, where you can kind of like just ask all your suppliers, ask all your energy providers, what is the emissions from generating like 1 kilowatt of energy, and then you multiply it by your usage or something like that. So there's like lots of different ways you could kind of quantify it, but as you can see, it might become very difficult getting the data from all those scope 3 emissions, right? Because there's so many different categories. You could also think about some data-driven estimates, which we'll look into it further in this lecture, and then also satellite data estimates. So can you see the emissions from space, and can you maybe attribute them to the different industries in different countries? So in order to especially use the data-driven methods, we're going to look into the machine learning applications for tackling climate change. And specifically here, we're going to look like into different kind of clustering methods. So as you probably know from the few previous lectures already, machine learning is very helpful for extracting different patterns from data, especially when you have a large amount of data. and it can do lots of things automatically and optimizing processes, but it also has some weaknesses. So it's very sensitive to your training data. If your training data is biased or maybe has some gaps, it might create results that are not necessarily realistic. It could be also poor at generalizing if the data changes. So if you train it on one company, but then you want to generalize your method for everybody else, it might not necessarily work for everybody. And sometimes it finds correlation where it should not really exist. So it finds correlation that doesn't have a real world causation. And that might be an issue as well. So let's think about this example now, where you can look into the reported emissions from different industries in different sectors. Like, for example, CDP database is like one of the databases you can look into, like what are the emissions disclosed for by different people. And then you can make some inferences on the emissions for an unknown company in a given sector. So for example, if I see a lot of my peers disclose scope 1, 2, 3 emissions, maybe instead of me trying to track all my scope 3 suppliers, I can just kind of do some inference and figure out I'm a similar company, so I'm going to have similar emissions. So this is one way of kind of thinking about how you can use machine learning methods for the scope 1 to 3 emissions, given that the data is really difficult to obtain sometimes. So let's say you have a food company A that already disclosed emissions into the database. You are a food company B, and you want to know what your scope 1 to 3 emissions are. Do you think this sort of inference method makes sense? Like, is this approach of kind of mapping emissions from one sector to another, or like from one company to another, is it going to be accurate or not? Okay, maybe we can see the answers. Yeah, all right. So some people think it's accurate, some people think it's not accurate, and some people say sometimes. And I think, yeah, the right answer is sometimes, and it really depends on what attributes of the data you use. Because yes, in principle, it could be very accurate if if the food company A is kind of very similar direct competitor, they are like similar size, sell similar products, sourced from similar places, like we're basically almost copies of each other. Of course, that could be very good inference. But it could also be very inaccurate if the food company A is like very small and I'm a very big company, or the other way around. So it really depends. The accuracy of this mapping depends what features do you use in making this prediction. And that's very important also, like, because the feature selection may kind of alter your result, right? So again, like, would you trust the answer? Maybe, maybe not. And here we can like look for a simple example. So like, let's say food company A is a large international company in California. So it's a very hot kind of dry climate, like there's specific energy sources, most of energy is renewable, right? So maybe they have quite low, like scope 1 emissions, scope 2 emissions are also very low, and scope 3 emissions are quite high, but they're trying to keep them low. Maybe your company B would be a small owned store in Finland. So the climate is very different. The energy use for air conditioning could be much smaller. Maybe there's some more energy used than for heating. Again, it's a much smaller company. Your suppliers might be very different. So even though you're both in the same sector, this mapping might not be really accurate. So I think whenever you use sort of clustering and mapping methods, you really have to think about kind of the end goal and like, does this make sense, right? Like, what am I predicting? Do those numbers actually make sense? And that's why I think with any use of machine learning method for more accurate predictions, you need to like really think about like, what attributes am I using? Do those attributes make sense? And then also, is the data biased towards one, maybe certain type of companies? So in this case, let's say if you use some additional attributes such as country of the company, country of the headquarters, number of employees, revenue, size, maybe like what are the main sourcing channels, like this is going to give you a lot more accurate answer if those things are like synced in, right? At the same time, it really depends what's inside this database, because if this database here has only very large companies that disclose emissions and you're the only small company in this database, the prediction is not going to be accurate. So also you need to be careful to know the data you use, what could it be good for? So maybe it could be good for mapping similar like for like companies, but then maybe it will not be accurate for mapping very different companies. So it's good to be always cautious about what sort of data biases are in your training data, because these biases are going to carry on onto your answers. And that's why there's several papers that kind of use different boosting methods. So in this case, like I'm always putting the references here, and I think they were also shared in the pre-reading materials. This one paper explores different features that are important for predicting category 3 of scope 3 emissions and how do they differ. So as you can see here on this heat map, you can like kind of use different attributes in your data and try to predict it, and then also like see how accurate the prediction is. And I guess the question is, does it make sense to use different features for each individual category of scope 3 emissions, and what are the pros and cons of doing that? So maybe take a few seconds to think about that. All right, maybe let's see if we can see the answers. All right, so I think here the challenge is that like including more attributes in principle could increase your predictability, but at the same time, having this many attributes requires all this data to be available in the database. So I think the challenge here is like sometimes companies don't necessarily disclose all those different numbers, right? Like they maybe only disclose emissions and maybe one or two attributes. So you can have a very accurate model based on a lot of predictors, but then your data training sample will be much smaller because not everybody discloses all this information. So it's a little bit of a trade-off of trying to make it really accurate versus having a lot of data to train your model on. And just also like trying to see what's the accuracy of this prediction, because maybe some of those attributes are actually not as useful. So I think this sort of heat mapping exercise can really help you to see how important each feature is, and then like the most important features maybe you can use, and then kind of you can fine tune your model to use the key features, but at the same time keeping it reasonable, making sure that all this data is indeed in the database or like easily available, because otherwise if you build like a very complex model but you can't really easily train it or apply it, then it's not really useful. Okay, so this is a similar example also of another way of inference of inference-based methods for predicting, in this case, greenhouse gas scope 1 emissions. Oh, sorry. And in this case, this paper also cited here uses gradient boosting decision trees. And then they also, again, use over like 1,000 features from multiple data sets to try to arrive those different like emission estimates. And I think, again, like there's a benefit of using multiple data sets, multiple features, but then also the drawback is that sometimes maybe the data is not available for different type of companies, or sometimes there's, again, like biases in this data. So it is still quite a bit of an active research trying to kind of optimize this, like how much data should I use, which feature should I use, and also are those emission estimates really accurate or not? Because if you want to know if you're truly net zero, you kind of really want to make sure that the numbers you get out of those algorithms are as accurate as possible. So the common challenges in the emission accounting space are imbalanced data sets, missing features, mismatched feature patterns, and then also like we need to quantify the uncertainty in the prediction. Just because the model says is this many emissions, what's the uncertainty on that answer? I think that's a very important question to look into. And then there's another paper that also uses tree-based methods, but in this case, they're also predicting scope 1 emissions. And you can see they have different target variables, predictors, and different data sources to kind of trying to arrive to those scope 1 to 3 emissions. So as you can see, I think it's a relatively easy machine learning task in terms of like the data. It's like a lot of data sources available, and then you can kind of select different features. And the challenge is only like knowing how accurate my answer is. So right now, there's actually several AI-based startups that offer this sort of service of like, okay, give me your company features and I'll predict your emissions, and then you will know what you need to do to go to net zero. But I think there's still a lot of room for improvement in ensuring that the answers they arrive to are actually very accurate, right? Because in the end, what the goal of this exercise is making sure that all the company's emissions are like as close to zero as possible, right? And whatever cannot be zero is being removed. so that ultimately everybody's net zero. So like we need to really have confidence in those numbers in the end. And that's where those sort of top-down estimates also come into play. So like so far, the methods we described were like bottom-up, right? Because it was based on a database where everybody discloses different type of emissions, and we try to kind of cluster them and make predictions. If you think about it from a top-down perspective, you could also use satellite data to kind of track greenhouse gas emissions with quite high accuracy, and like climate trace is one of the examples. And I think there's like other satellite data products now as well available that do similar things. In this case, you can leverage machine learning to like kind of fill in the gaps in the current emission data and provide near real-time estimates. And it can also improve this kind of self-reported emissions, reducing the risk of underestimation and inaccuracies. So in principle, you could kind of use both. You could use the bottom-up method. You could use the top-down method. And ideally, those answers should be very similar, right? Because then you know you're probably right if both very different methods arrive to the same answer. And in this case, this could be useful both for like company level emissions for different sectors, as we discussed earlier, but also for different countries, right? Because different countries also have net zero targets where they need to kind of reduce their greenhouse gas emissions, which is both CO2 and non-CO2 emissions, and make them as close to zero as possible, and then kind of remove whatever is above zero. So this is just to give you an idea that there's top-down methods, there's bottom-up methods, and it's really important to kind of find this middle ground and be able to really discern what's happening between those emissions. And as we kind of now move forward to the third part of the lecture, what are other applications of machine learning for emissions monitoring? So here, like, well, we already found like, okay, you can account for your own emissions, bottom up or top down. And then how can you remove those remaining emissions that you couldn't easily reduce? So there's like several machine learning approaches also that can help us to monitor the nature of nature-based solutions, so like nature-based carbon removals, for example, and offsets. And also there's a lot of machine learning applications for monitoring biomass changes and deforestation, which again kind of links a little bit with another lecture on the MRV for the forestry. So I think this is going to be a little bit more like hands-on applied cases that are also like related to this lecture. But I hope you can see this connection that like, yes, emissions accounting, you need to be net zero, but then to be net zero, quite often you need removals, and a lot of the removals are actually right now nature-based solutions such as afforestation. So here is an example of a data pipeline that uses machine learning products to predict the amount of biomass from space. So of course you can see it from a satellite data, but like the satellite sees different aspects, for example, vegetation growth, like what's the surface cover, what kind of plants are growing there. And if you want to know how much carbon is being stored in each grid cell, you kind of have to use different sources of satellite data, right? Like it could be NDVI, vegetation index, like some other indices. You can kind of merge different satellite data as your inputs. You can also use some bottom-up in situ observations that are based on like specific measurements, how much carbon is being stored in a given tree or in a given type of species. And then you can also use like allometric equations to kind of scale it up. So you can use, again, bottom-up, top-down and bottom-up approaches as your predictor variables. And then you use like different machine learning methods to kind of aggregate this data and make predictions. So the goal of this methods, and there's again like several data products available, is to kind of have an idea of how much biomass and how much carbon is being sequestered in any location on the planet. Because if I bought carbon offsets or carbon credits from an afforestation project in a given location, I want to know, is this still like, is the biomass still being growing there? Is the carbon being sequestered? Maybe something happened to this forest. Maybe it was deforested. Maybe there was a forest fire. So I want to have a kind of good idea that the removals I bought are actually still there. So this is one example of a pipeline for like the sort of like remote sensing based biomass estimation of various kind of species. In this case, they are focusing on a tropical forest in this paper. So what maybe just like think about for a few seconds, like what are the sources of uncertainty that could be related to this predicting biomass from space? What could kind of go wrong in those predictions? And what are the challenges with those data sets? All right. Yeah. So hopefully you could think about some of the uncertainties, and we're going to cover some of them in the upcoming slides. So here's actually an example of a very recent biomass data product that uses machine learning to generate a granular global data set of biomass. And you can see this is a very granular image based on like collaboration between different institutions. They are trying to like have a 1 meter resolution, which means it's a very granular product covering the entire kind of global coverage. And they are measuring vegetation canopy height for all vegetation that is taller than 1 meter. So they are trying to see like what's the height of vegetation. And if you invested, let's say, in a afforestation project that is used for your carbon removals, you want to see that the trees are still growing there and they continue to be growing. So the principle of the idea of creating this data sets is very useful because we need kind of like real-time easy tools to observe what happens to those different nature-based solutions, and are we actually growing more trees, for example. And there's this kind of evaluation of this data set, as you can see from the Earth Blocks review, which I think is really helpful because it really triggers different kind of critical thinking sense about this data set. So there's several pros and several cons about it. So there's of course like the pros you can kind of read here. It is like the only tree level canopy height model available for the whole globe because it has a global coverage, which is really good. You're not concerned like about specific location, only it like covers the entire globe. You can see individual trees on it because it's very granular. Since it's like in this case, they use canopy height instead of biomass, you can kind of use your own allometric equations to be able to convert it to biomass. So it makes it like very confident, more confident in the results. And the underlying method is very detailed in a paper that they publish with it. And you can also use it for some other tasks, such as ecosystem fragmentation, for the biodiversity scores, and forest carbon stock. So there's a lot of good things about this data set, but at the same time, you need to put your like kind of critical thinking hat on and think about how was this data set derived and does it make sense? So while the global data set coverage is really good, actually, because it's global, it might have some performance biases and might perform poorly specifically in a data poor region. So while some of the data is like more available in one location than another, so it doesn't necessarily mean that the quality of this global data set is the same across the globe, and like some regions might actually be more data poor. It also like may have some challenges with the areas that are with persistent cloud cover, for example, or if there's like no canopy and there might be some errors happening there. And those areas are not really flagged in the data that this area could be like a difficult to predict. So it'd be really helpful to also have a mask which tells you the confidence of the results, which areas are more confident in the prediction and which ones are less. And then also, I think the main challenge I found with this data set is lack of temporal consistency, because they are training data over like a very short time period, and they are aggregating different years together. So, I mean, different trees can be of a different height in a different year. And if you use this entire kind of period as your training data, you're like mixing different things. So because you're like, here they're only predicting one thing, canopy height, but they don't have this temporal resolution canopy height in a given year, it makes this data set a bit less useful, because what's really useful is to actually have the time series of how this canopy height evolves over time. So of course, there's like room for improvement of how to make this even better in the next iteration. And here's another example, which is very similar, by using a different data source of also trying to predict, in this case, biomass data products, also from space, where again, like they use NDVI or like JEDI satellite data, different sort of like satellite inputs to you as your training of your model, and then they're trying to predict how much biomass is kind of like in a given location. And you can also compare those results with, I mean, just Google Earth images. So if you look into Google Earth, for example, there's like a pre-fire and post-fire area of a forest in California, and then there's like a fire event happening, right? So you can see that like in this case, already the biomass was kind of slightly on a decreasing curve, as you can see the trend. But after the fire, some of the data sets immediately react and kind of see, oh, there's a huge decrease in biomass, while some other data sets have a lag and react only end of the year or end of 2 years after the event. So there's also like a bit of a lag in terms of using actually like pretty much the same input data, but depending on how you connect it together and what your machine learning algorithm does, you might end up with very different results. So overall, I would say what the good news is that all of them kind of show decrease in biomass, which is good. But on, in a sense, the improvement side, you can see that some of those data sets are really lagging and like need to be possibly having better temporal resolution to be able to predict this better. So again, like why does this really matter? It's like if you want to be net zero in any given year and you keep buying like carbon removal solutions or afforestation projects, you want to make sure that they are there every year and then they are growing, or like at least they are not being damaged. So I think it's really again like large area for lots of research and lots of work in that space. So finally, we kind of like arrived to like summary of this lecture, which is just thinking about the challenges and future directions of machine learning applications for emission accounting, and like also this kind of biomass monitoring, which is also related to emissions, because if this biomass is being damaged or destroyed, it releases carbon back to the atmosphere. So as you like think about those different methods, it's always good to focus on like thinking what are the main benefits and what are the main drawbacks, but also always keep in mind like what are the alternatives, what else could I do? Maybe there's a simpler method that would be just as accurate. And then if you have a very complex machine learning model, how do I know if I can actually trust this prediction? So I think the most important one is like cross verification of your output data with observations or with some other source, just to know how confident can I be in the results that the machine learning model is producing. And I kind of like to use this sort of matrix of difficulty versus impact in assessing different solutions, because if you think about there's like an easy solution to implement that has high impact, then definitely it could be like your preference. So sometimes a linear model may be just as good as like a very convoluted and complicated machine learning model. And if the predictability is similar, it's better to go with a simpler model because you can understand better the drivers and how the model works. At the same time, some problems are really challenging and difficult, require lots of input data sets. So you do need like a lot more complicated infrastructure of the model to build it. And it might have much higher impact as well. So if it's, as long as the impact is high, it's okay. But if there's an easier solution, maybe it's better to use the easier one, which you can understand better. And then again, I think the worst space to be is here, which is like, it's a very difficult, complicated model, and it like predicts something that doesn't make sense, even like no one's using it. Like it's very low impact. So that's kind of a waste of computational resources in a sense, and it's best to avoid being in that space. And I think, as you probably know from the other lectures as well, machine learning is only one piece of the puzzle. So it's not it is a powerful tool, but it's not the silver bullet, and not every problem is necessarily relevant to it. So it's really important to figure out, should I use machine learning or not? And should I use it, how to use it best? And the way to use it best is actually to collaborate together with the experts in the domain field. So there's a lot of experts who maybe study emissions directly, climate science, like biomass. And if you're developing some of these products, you kind of want to probably collaborate with those domain experts, which maybe don't know much of the machine learning techniques, but they bring a lot of domain expertise. And that way you can ask them, okay, what is the questions I should be solving for? What are the main challenges in the input data? And to fully understand the data biases and then also the uncertainties that your model might be having. So I kind of provided also a list of resources of the different emission data sets and like papers that you might find interesting if you find this space interesting. And hopefully you learned something new today, and also you got some inspiration of what are interesting research directions to pursue. So I'm happy to kind of stop sharing the screen, and we can maybe look into the questions and answers and see if there were any questions here. Okay, so there is several. Thank you so much for the feedback.
Thank you so much, Dr. Kasia. Is there any question from the audience for the session?
Okay,
Can
so
please ask
there's several questions in the Q&A, and I think the first one maybe okay. How is my opinion whether greenhouse gas or emission accounting should maybe replace the product life cycle from the ingredients to still recycling? Well, I mean, I think it's not necessarily either or. It's more like a lot of those life cycle accounting is really difficult because sometimes there's like missing data, or you don't know how to kind of predict it. So if you have direct data available, of course, use the simplest method. But if there's data missing, I think machine learning provides an interesting alternative for like clustering the emissions and predicting them in different way, and possibly what the goal is to hopefully have the same answer or as close as possible to the life cycle analysis. Then yeah, there's like some more comments on the like remote sensing being also really challenging. Yes, of course, like if you think about like remote sensing, so if it's like bottom up, like in situ measurements, that's really time consuming, labor consuming, and expensive. Like you can do it locally for a small projects, but then if you want to know it on any location on the globe, it would be nearly impossible to assemble this data. But at the same time, what the satellite data, they provide like a lot of different metrics, right? Like NDVI index and like some other kind of like soil moisture, different sort of layers. But you also need to know, first of all, how to kind of interpret them. What are the limitations of its layer? Because some of them maybe are showing something that is not too visible. Like I had several examples in my work. For example, when you look at the fire data from NASA, for example, you see like all the different fire spots. But sometimes if the luminosity of this fire is really high, or if there's like clouds over the same area and then the luminosity becomes much higher than it really should be, you can get kind of false positives. And similarly, this happens like also like with just monitoring surface cover from space. For example, if you have mangroves, which is a very kind of like efficient way of sequestering carbon, and like a lot of blue carbon solutions are based on like mangrove plantation, you really cannot easily see it from space because they are submerged in water, and then the water reflects sun, and then this reflectivity makes this data really difficult to see. So I think there's like a lot of challenges both using satellite data, which we like, there's lots of research in this area, like how can we avoid those common pitfalls, and like how can we make the data more accurate. And then there's also challenges with the bottom-up approaches. So I think linking them together is, of course, really good. But again, it's a very active area of research right now. Okay, do any of the models take into account peak power plants? I think that may be more related to the climate trace. I believe yes, but I think the best way to find out is like look into the climate trace methodology, and I think they probably would look into it. Does machine learning for biomass work just the same as deforestation monitoring? Yeah, I would say it's very similar. I would say, so deforestation monitoring, like you can do it in different ways, where you can look at the surface coverage, and like, is the surface coverage decreasing, right, for example. So that might be an easier task to do than like predicting biomass, because biomass is more like a derived product. So you look into like, what is the species, kind of what's the coverage, what's the canopy height, how much carbon is being sequestered. So I think biomass data products, maybe they're like more challenging to compute, but then also they provide a bit more useful answer, because I think the deforestation monitoring, yes or no, it's easier, but it doesn't tell you how much carbon is being stored or lost. It just tells you, is the forest there or not? Well, there's a huge interest in biomass products because they want to know, okay, if there's a afforestation forest growing, how much extra biomass is being kind of grown each year. Like, we want to have a quite granular view on that as well. What are the criteria and index to estimate the outcome of machine learning? I mean, it really depends on each project. So I think what's really important is to know, what are you trying to predict, and kind of like, is your answer correct or not, right? So what are some other ways you could cross-check your answer? Like, if you make a prediction but you don't know how to cross-verify it, then it's not very that useful. So you always need to kind of like see what's kind of like the ground truth, and then compare your data through different statistical methods. And like, how do you actually, what sort of statistical test do you use? It really depends on the type of data you use. So I think it's very case specific. And it's always, that's why it's always good to kind of collaborate with the domain experts to be able to kind of address those questions, and also be aware of the common pitfalls. Because I see it like also a lot in the climate data space. A lot of the climate data from climate models is widely available, and I think your previous lecture with Kai was actually on the climate data and machine learning, and that's where you also need to be very careful in knowing, what data do I use as my inputs, and does the output make sense? Because there's a lot of phenomena in the climate system that this data might be subject to, like the El Nino array, like some other kind of oscillations, and you need to be able to be aware of those trends in the data. do any of the models take into account plant CO2 input and CO2 output as the plants themselves? So I would say the models we talk today don't necessarily take it into account. They only look at the total amount of carbon stored in the biomass. But if you're interested in like kind of like a plant specific developing a model that is it's called more terrestrial vegetation model. There's a lot of models like that that are like really plant specific, and like how much CO2 is being taken up, how much oxygen is being taken on, and like what's the efficiency of photosynthesis and the kind of CO2 saturation effect when you have maybe like too high CO2 in the atmosphere. There's a lot of models like that. They're called, I would say, dynamic vegetation model or terrestrial vegetation models. And then they would be mostly used in those kind of comprehensive climate models that were discussed in the previous lecture, from what I am aware. How about the war emissions and military experiments? Honestly, I think it's an important question. I don't know the answer. I think, again, it might be quite difficult to quantify it. Maybe if you can see it from space. I don't think they really disclose it, but that's not my area of expertise, unfortunately. Yeah, how can you leverage both ground sensors and remote sensing? Can this make models more accurate? So exactly, like, I think there's a lot of effort in doing that. There's like several initiatives and projects that are trying to do it, exactly because you can kind of, in a way, fine-tune your machine learning model that is being based on remote sensing data to be able to have this observational constraints from remote sensing to be more accurate. I think that the only challenge of those models, which some of them already exist in the data products I'll show you, is that there's very kind of limited amount of ground sensors and ground data. So even if you fine tune your like global model to those like few locations, you might be very accurate in those few locations, but you might not be necessarily accurate in other locations as well. So yeah, it would be great to have like a much wider and global data set of remote sensing measurements. I think it would largely improve the quality of many of those products. Okay, and are there any specifics using satellite data to determine ecosystem changes from 2014 to 2024 in a particular region? So I think, I mean, it really depends like what ecosystem changes you're thinking about, like, right, is it terrestrial, is it aquatic? There's like specific data sets you could use for. I think that's 2014 is a good period to use, because anything past the year 2000 or 2014 actually has a lot more data set from the satellite data. So I think really what's important here is to know what are the best use cases and what are the limitations of each data source, right? And then like, which data should I use? Because there's a lot of, even satellite data, there's a lot of products available. So it's really figuring out like what sort of ecosystem changes you're interested in, and then what sources of data should you use given its kind of pros and cons. And sometimes you might want to use like, you know, multiple data sets that kind of predict the same thing differently to see what's the range of your uncertainty, because sometimes only selecting one product will have certain biases, but if you kind of maybe do it twice using different data products, you will see like what's the spread, and then this will give you an idea of how uncertain your answer is. But I think, yeah, definitely is having access to the satellite data, and there's again a lot of tutorials how to use it. All of it is like publicly available. There's like a lot of research questions you can answer with it. One tip I can give from my own experience is, because a lot of those data products are like huge, right? They're kind of divided into like small areas or small grid cells. So if you're interested in a specific ecosystem in a specific region, only download the data for that region, right? Because you don't need to download the entire global data to process it. So that might be a kind of processing tip. Yeah. How do you validate model output if you have sparse observations? Yeah, I mean, that's a challenge definitely a lot of those products have. And I think they do a lot of validation with the observations that they have in the regions they have. But again, like in some other regions where they don't have observations, it's really difficult to know if that projection is correct or not. So that's why I think having the sense of uncertainty, what regions are more confident than others, would be really helpful. And okay. How can we use machine learning to deduplicate scope 3 emissions of companies in the same sector, since that will be overlapping? I'm not sure if they will be overlapping, because I mean, scope 3 would be overlapping with scope 1, right? But like, if you're only doing scope 3, the same sector companies, they might be having the same emissions, but that means they both buy the same amount of products. So I think scope 3 emissions themselves are not overlapping. And then even if the companies are the same, actually, that would be like, I mean, think about your twin company, right? If it's identical size company in the identical kind of setup, then your scope 3 emissions might be quite similar, right? So I think that's, I don't know if I understood the question correctly, but that would be my answer. So yeah, I mean, like, I think somebody commented that, like, yeah, definitely, like, machine learning is still in its infancy in the space, and it has a lot of potential in, like, kind of making those predictions more accurate. But I think the main challenge is right now that there is very limited training data available. And, like, yes, each year the disclosure space becomes bigger and bigger, so more and more companies are disclosing. And I agree with the comment here that, like, right now, using machine learning data, the kind of models on a very sparse data set, it was quite uncertain. So I would personally recommend that if you can quantify the uncertainty, then it's okay, you could use it, but it would be quite difficult to just use machine learning model to predict your emissions, not knowing how wrong you could be, right? So yes, it is a lot more laborious and difficult to be, like, doing it by hand, bottom up, right? Like asking all your suppliers for the emissions. But in a sense, we do need this effort to have enough of this grand trove of observations, in a sense. And then you can kind of improve the accuracy of the machine learning models. And it's also important to remember that even observational data set, whether it's like remote sensing data, like, you know, and then in situ observations, or if it's your direct kind of bottom-up approach of scope 3 emissions, it's never going to be 100% accurate either, right? Because there's always somebody who maybe missed a zero or put the wrong unit in their emission accounting, right? Because you have to account different greenhouse gases together into CO2 equivalent. So, like, there's errors on both ends. So sometimes even your observed grand truth might be sometimes wrong. So it's a huge challenge. There's a lot of research in that area, and definitely it's a very active questions to be asking. So, okay, another question. Using allometric equations to calculate biomass, is it possible to calculate CO2 emissions from certain crops? How do you predict it, and what resources can you use? So I think definitely you can calculate CO2 emissions from different species. And I think whether, like, yeah, how much CO2 to take up, like take in. So that's CO2 being stored, and that's what allometric equations tell you, like how much carbon is being stored in the above ground biomass and below ground biomass. And then if you want to predict emissions from the crop, so I think what you mean here, if once the crop is being harvested, how much CO2 is being released. So I think that definitely can help you. Those equations could be helpful in this prediction. Let's also remember that, like, for a lot of the agriculture kind of agroforestry applications, it's a bit challenging because sometimes the tree is still there, and, like, you pick up only, like, the coffee beans, or you only pick up some parts of, like, fruits of the tree, but you don't necessarily cut the whole tree down. So in this case, the tree is kind of still there absorbing carb. But I think, yeah, there's, like, definitely different methods for accounting for it. Just one thing to note is all these allometric equations are very species located and location also specific. So even if you have the same species planted in different regions, it might have slightly different kind of amounts of carbon being absorbed. Yeah. Okay, and then do any of the models take CO2 ocean emissions? So in those specific use cases we talk about, the answer is no, because we were only measuring company emissions that go to the atmosphere, and we were also measuring the biomass that being sequestered on a terrestrial land. But the models that the previous lecture with Kai on climate models was talking about, those models also model absorption of CO2 by the ocean. And then there's also sensitivity to the alkalinity and acidity, right? Like how it changes. So yes, definitely you can have a model of CO2 sequestration in the ocean and how it changes. It's part of this kind of like those global climate models or regional climate models, but the models we discuss in this lecture don't focus on the ocean. Okay, machine learning for carbon removal is easier, but what about for offsets other than forest monitoring? So I think maybe the reason why I specifically focus on carbon removal is because my motivation was going to net zero, right? So you have emissions that are going to the atmosphere, so either you stop emitting, or whatever you're emitting, you have to buy a removal that is removing the amount you emit. I think the offsets are like, in a way, intermediate solution because they they only stop emissions, but they don't actually remove those emissions. So if you just buy offsets that are like maybe cook stoves or like some other ones, these are good initiatives, but they don't actually remove CO2 from the atmosphere. So that's why I haven't focused on it. And to be fair, I don't actually have much knowledge on machine learning for offsets that are not removals, because my main focus is on the carbon removals right now. Okay. What's the viability of machine learning in assessing biomass in the marine ecosystem? I think, yeah, that's an interesting question. And again, I think it'll be quite difficult to do it using space data only because of all this reflectance of water and kind of other challenges, how we see the ocean. I think for that, because the ocean is so deep as well, you would need some of the process-based models that are like part of those climate models where you have the ocean circulation. There's like a lot of layers, like a lot of those models would have 20 layers or more of kind of water levels. And in each water level, depending how much sun is there, there might be photosynthesis happening. Then like some of the, either if it's like, biomass, or like it's kind of like the zooplankton is like going down and circulating. So there's a lot of processes happening in the ocean itself. I think having only top-down view from the satellite might not tell you the whole story. So I would highly encourage you to look into those kind of ocean circulation models, which some of them focus also on the biogeochemical cycle of the ocean. There's an entire kind of area of modeling of that. So I think that might be kind of interesting thing to look into. Since you mentioned soil moisture, what are my favorite sources for soil moisture? I mean, it really depends on like the data product you use, and like also like I don't want to like endorse any specific sources, but I think for any satellite-based data or any public data source, always look into like the papers that describe how was it created, and then think about like what is it useful for and what it shouldn't be useful for, because it also depends what's the resolution of soil moisture you need. If you only are interested in a specific region, then of course regional data might be much more accurate than a global data set. But if you're looking for a model that is a global coverage, then you are kind of stuck with those bigger data sets that maybe are like less resolution. So it really depends on your question. How have non-CO2 sources affected CO2 budgets over the past 5 years, and what's needed over the next 5 years? So I think, I mean, the non-CO2 sources are like right now, what we call by emissions is kind of CO2 equivalent. And there's different ways of converting non-CO2 emissions to CO2 emissions. The different disclosure bodies, they have specific equations how you convert it. But basically, yeah, like you need to reduce all the greenhouse gases, which is both CO2 and non-CO2 emissions, to be fully net zero. Okay, and maybe one of the last questions. Okay, I think. All right, so I think maybe the last question. Let's pick this one. In practice, do you think the lack of quality data sets incentivizes companies to avoid ecosystems of certain areas? To be fair, I don't know. I think there's like a lot of things that people consider, not only the quality of data, but also there's a lot of like those kind of co-benefits, right? So ideally you want to have, if it's a nature-based solution that is like afforestation project, it should also have like local benefits. It should have like, biodiversity benefits, local communities involved. So there's a lot of aspects that look into it. Of course, if there's a project that has no data at all on any of those aspects, it'll be quite hard to be like trustworthy. But I think, yeah, like having more data and more transparency in the different projects really increases the incentives of like, oh, this is a good project because the quality can be justified in certain regions. Yeah, well, thank you so much for all the questions. I'm afraid I don't have time to answer all of them, but feel free to connect on LinkedIn, and I'm happy to help in any way I can. It was a pleasure giving a lecture here.
Thank you so much, Dr. Kasia Tokarska, for such a nice talk and answering all the questions, queries of all the participants. Thank you so much. All the participants, please, the link for the feedback have been updated, and you can now fill the feedback form. It is.